So if you notice that we only have two more sections before we're done with chapter 4. And that's 4.5, 4.6. We're not going to go into 4.7 or anything like that. Those are some other types of application that you could look up. But we'll see applications in 4.6. So 4.5 is all about solving exponential equations. Now, we have worked with exponential functions and logarithm functions, but we have not necessarily worked with solving them or solving for x in an equation using those kind of functions or terms. So we're going to be doing first the exponential and then the logarithm. Now, if you guys need any practice on these translations for logarithms or these rules of logs that we work with, because it's going to be very necessary when we're solving these, you need to know them by heart. You guys can always ask me, and I have some practice that we can work with. Otherwise, the practice that you guys will see are the review test, chapter 4 test review questions. And I hope that you guys do that. I'll make a discussion board with that as well. So, solving exponential equations. There are main two types of exponential equations that we are able to solve without even working with anything new. So the first one might be something like 5 raised to the x equals 125. We're able to solve for x here because we've seen problems like this before. We've seen 5 squared, 5 cubed, 5 to the fourth. Maybe not all the way past the third power, but we've seen most of it. So we can kind of guess that it's x equals 3. We can guess and then we can verify. That's kind of like a guess and check idea. Well, another type of problem that we have is, let's say I had instead 5 raised to 2x equals 5 to the x plus 1. Just giving it some time for thought, you should be able to solve this out for x. And the reason why is because both of their bases are the same. So what are you really doing at the end of the day to solve for x? You're going to be setting this guy equal to this. The exponents have to be equal to each other. So why not set them equal to each other? 2x equals x plus 1. And then if I subtract x to both sides, I get x is equal to 1. You can verify these will work out if you plug it back into your exponential equations. Now, these are some problems that we can work with already. However, there are issues with them. The first one in particular requires us to kind of guess. We kind of have to know what that x value is already. What if I said 5 raised to the x equals 6,025? Would you know what value of x that should be? What if I instead said 5 raised to the x equals 149? Now we have a decimal exponent. Can we work with that? Those are much harder problems that we need to tackle. And then on the second one, maybe I might have some other terms. Maybe I might have 2 plus 5 raised to 2x equals this. How do we deal with that? These are some issues we got to discuss. So, let's work with these. These are going to be calculating how to calculate equations. So we're going to be working with problems like this. 8 times, let's say Euler's constant, raised to, let's do 2 to the x equals 20. Looking at this, just looking and glancing at it, this is not a simple problem that we can tackle. It's not. However, there are ways to actually solve these exponential equations, and it's going to introduce the idea of inverses. So, to deal with the exponential equations first, it is very helpful to deal with it the same way we did absolute value equations initially. When we worked with absolute value equations or inequality, I always told you to isolate the absolute value. The thing that is the hardest to deal with, get that by itself to one side of the equation. If you can get it to one side of the equation, you might make it slightly more simple at the very least. At least you're only working with that tough term rather than a bunch of terms matched up together. So, isolate exponential function term. I'll say term. I'll say term slash factor. And I say factor because sometimes it's not. It's still in that term. So looking over here, we need to somehow isolate e raised to the 2x. That's their base and our exponent. We need to isolate everything that is not in the base and the exponent. So that means I gotta get rid of the 8 somehow. Well, the operation with the 8 is multiplication. So the undo multiplication is divide by 8 to both sides. If I divide 8 to both sides, I get e raised to the 2x equals 20 over 8. See, now, even though I still don't know how to solve this equation for x, I've somewhat made this problem slightly easier. And let me just erase this because it's bothering me how the 20 looks, or the 8 looks. So, we've worked with canceling things out. And should be nothing new. It is only new in notation and symbols. To cancel things out, we've always used the inverse operation. The inverse of addition, subtraction. If I had x plus 4, I subtract 4 to both sides. If it was 2 times x, I divide 2 by both sides because that's the inverse of multiplication. If I said the square root of x, you would square both sides because squaring is the inverse function of square roots, as long as you restrict this domain, of course. Now, what is the inverse function for an exponential e to the x? We've worked with that before. If we scroll all the way, oops, this is not even the right page. If we scroll all the way previously, we've talked about inverse. We have. The inverse function of e to the x, if we look all the way back here in our notes, and it's very far back right here, we said, hey, it was ln. It was natural log. Why is it natural log and not any other log? Well, because natural log is log base e. And clearly our base here is e. So what we're going to say is, for the second step, we're going to apply inverse logarithm. So let me make this font better. To both sides. Now, when I say apply logarithm to both sides, I mean you apply to every term on the left side, every term on the right side. I know a lot of us made a mistake on that test when we were finding inverse, and you guys had to multiply 5 to both sides, and then some of us only multiply 5 to one term. You have to multiply to your entire equation, which means you distribute that 5. So I'm going to apply the inverse logarithm of e to the x. And the inverse log is log base e, or we can say ln. Let me use a different color. Maybe I should just change this side. Yeah, I'll change this. Oh, no, it's a good size. ln. And I'm applying my natural log to both sides. And then the first side is e to the 2x, and the second side is 20 over 8. Oh. So I apply it to both. Why would I apply it to both? Because remember, our logarithm function is the inverse of our exponential function. If we choose the right inverse, we have a property. This is exactly equal to 2x. Another way you can think about it, you can also think of it as cancellation. This turns into 1. So we're good to go. They cancel out completely, and we're left with just 2 to the x equals ln 20 over 8. So it's very important you understand these rules. You can think of it as cancellation. Technically, we can treat it as cancellation. Some people don't, but it's perfectly fine. Now, it should be clear that we have to divide 2 to both sides to solve for x. Now, be very careful. Over here it says ln of 20 divided by 8 divided by 2. You cannot divide that 20 by 2. You cannot divide that 8 by 2. This is in our input. Those are what we're throwing inside of our function. We cannot divide what we're throwing inside of our function by 2. No, we can only mess with its output. It is a function at the end of the day. You don't know how this plays inside of our function. So leave it be and work with the output instead. So the final thing to solve these exponential equation is solve. So the main thing that is new is applying the specific inverse logarithm. We've already worked with isolating specific functions or terms, and we've worked with solving. It's just now applying that inverse log to both sides. Now, of course, you got to plug it in and check your answers, but that comes a problem later on when we get into logarithms, not necessarily exponential. So boom. And you can calculate this in your calculator. If you want to calculate it in your calculator, let's hop on to decimals and everything. Thankfully, this is natural log. So this is easy to calculate. We can do natural log of 20 divided by 8, all divided by 2. And that gives us our approximation for x. 0.46. Let's just round it to 2 decimal places. Oh. So we're good with that. That's one type of exponential function we need to be able to solve. Well, what happens now if, I gave you something different? What if I gave you another example? Let's call this example. What if instead I gave you something like, and this is going to be a lot of me just throwing examples, so you guys have a lot of practice and everything. 3 raised to the x plus 2 equals 7. All right. So I encourage you just to pause and just think about how we're actually going to approach this. This is already isolated. So what inverse log function are we going to be using? Are we going to be using natural log ln? Are we going to be using the common log? Are we going to use log base 2, log base 3, log base 4? Are we going to use log base 7? What kind of log, what base for our log function we'll be using to cancel things out? So I'll let you guys think about that and pause it. All right, so if you actually thought about it and everything, we'll notice that this has a base 3. Some of you guys might have thought to divide both sides by 3, but unfortunately we cannot divide both sides by 3. Remember, this is an exponential function. We can't just divide the base by 3. We don't know how the exponential term actually plays out. It's not necessarily if I divide 3 to both sides, things will cancel out. No. So in this case, you should have known it's already isolated. But the inverse log you should have applied is log base 3 because this has a base of 3. And I'm going to throw whatever I had on the left side and the right side inside my function. This is 3 raised to the x plus 2, and this is 7. Now immediately you should identify that, hey, over here, this base is the same as this base. Well, they cancel out. Remember that. They cancel out in that manner. So you're just left with x plus 2 is equal to log. Unfortunately, nothing cancels out on the right side. And it shouldn't, unless we got lucky. Boom. Log base 3 of 7. And then to solve for this, we can subtract 2 to both sides. Now, be very careful. I am not doing 7 minus 2. That is inside my function. So I have to leave it outside my function. I can only subtract the outputs. Boom. Be very careful on that. Now, this is a problem. What if I ask you to calculate and round to the nearest 2 decimals? How would you even calculate this in your calculators? That becomes a problem because we don't have base 3 in our calculators. Well, if we looked back earlier, we have a way to work with bases that we do not really like. And to deal with these bases, what we can do is, instead, we can write this as x equals, we can use the change of base. If you remember what the change of base says is choose any base you want to use. I am going to choose log base e. That is the base I am going to choose, ln. And we have to write it as a ratio with the base and the input, where the input is my numerator and my denominator is my base. Boom. I choose any base I want. You could have written this as log 7 over log 3. You could have written this as log base 2 of 7, log base 2 of 3. You could have written this as log base 7 of 7, log base 7 of 3. The issue with any other bases besides natural log and common log is that you can't put it in your calculators. So it's very helpful if you choose natural log or common log. Minus 2. Again, we can't subtract 2 from it. We have to actually calculate this guy first, then subtract 2. So x is going to be approximately equal to whatever that is, and we can actually verify that. ln of 7 divided by, ln of 3 equals, or minus 2. I'm getting the entire thing and subtracting by 2. Be very careful when you do that. Now, if I wanted to verify to see the change of base formula is correct, let's just do log base 7 divided by log. You notice that I'm using a different base. I'm using base 10 this time. Base 10, the ratios of the base 10s, do I get the same value if I subtract 2? It's the exact same answer. So that tells us that it doesn't matter what base we're going to be using. They're all going to be the same values at the end of the day, as long as you choose the correct base. And I'm just going to round this up to 3 decimal places because I just feel like it. And of course, on test, I will specify how much you need to round off to. So we get negative 0.229. Perfect. We're able to solve this guy out, even though it doesn't have a base e like over here. It had a base 3. But we're able to solve that because we can choose any of the log function, a branch of the log functions, which is 3, and it'll work out. So you have to know which function you're working with, and you can tell by its specific base. So we'll go over do some more practice. Let's do one more practice problem, and then you guys can get more practice from the review, or you guys can email me to ask for more practice. I am perfectly fine with that. So another one we might see is, let's work with e to the 3 minus 2x equals 4. So you can pause the video, you can give this an attempt, and we'll come back in a bit. Alright, so if you tried this out, you'll notice that e is already isolated. Thankfully, the 4 is on the other side, so we're perfect. All we need to really do is apply our natural log function. So I'm going to apply ln, which is base e, because I have e over here, to both sides. And I like to do my ln notation first before I write anything. That way I can know exactly what I'm doing. Alright, so now that I have this, I can actually cancel this out. I'm left with 3 minus 2x equals ln of 4. You can calculate ln of 4, but now let's solve for x. And I'm hoping everybody's algebra is strong enough now that they realize there's 2 terms here. I need to get rid of that term first, which is the 3. To get rid of that, I subtract 3 to both sides. I am immediately left with negative 2x equals ln of 4. Minus 3, I'm left with a single term. Now I just gotta isolate the x through division or any sort of thing, maybe square rooting or whatnot. But I'm done with all the adding and subtracting. So now I just divide by, negative 2. So I'm left with x is equal to ln of 4 minus 3 over negative 2. Now, you might see your answer as, these are alternate forms. They are still correct, just alternate forms. You might see it as negative 1/2 ln of 4 plus 3/2. You might see it as that. You might also see it as, what else? What other ways can you really see this? Well, I guess there's other ways too, but you can see it as 1/2 times ln of 4 plus 3. You can see it as that way too. Just know these are all alternate forms. They all are equivalent to each other. I'm just rewriting it and expanding it and whatever. I accept either or. So this is what value you have. Now, you can calculate this out in your calculators. So go ahead and write that out. You can use any of the forms that we discussed over earlier. So I'm going to do 1/2 times ln of 4 plus 3. And then I get this value for x. And then, of course, you can verify this and whatnot. So x is equal to, what is that? Negative 2.19. So we're good to go on that. Now, few things that I want to address before we even move on to the more difficult problems. Let's suppose I had e raised, why do we even try to isolate? Let's talk about that. Let's suppose I had e raised to the 4x. I'm not going to actually solve this problem out. I'm not actually going to solve it, but I'm going to give you an idea. If I had this and I did not isolate the e, if I did not isolate my exponential term, what's going to happen when I apply ln to both sides? I have e raised to the 4x plus 3 equals ln of 1. This is an issue. We've never worked with any sort of addition or subtraction inside my natural log. We have not worked with that. We have talked about finding a domain, but we have not worked with solving with that. That is much more difficult to deal with. When there's more than one term inside your natural log, I can't cancel it out. I can't just say, hey, I'm canceling this. I'm done. No, that does not work at all. So be very careful when doing these problems. Isolate your base first. If your exponential function or term is not isolated, you will have issues and you will make mistakes. Because I have to apply it to both. I have to apply it to the entire left side and the entire right side. I'm not putting two different logs or anything like that. You can't use the idea of distributing either. So that is an issue. Now we work with something that we can work with, but is also slightly more difficult. Again, old stuff will appear. This is solving exponential with quadratic. Solving exponential with quadratic exponents, pretty much. So, in the case, what if I had an example like e to the 2x minus e to the x minus 6 equals 0. And I ask you to solve for this. Well, you might think of isolating it. You might think, you don't have to write this down, but you might think that you could do e to the 2x minus e to the x equals 6. You might think you can do that. And you have a good mindset. The problem is there's two terms here that are both exponential functions. I can't combine them because they're not like terms either. I can try to factor. If I factor in e to the x out, I'm left with e to the, what is that? X minus 0, or I'm sorry, minus 1. I can try to do that. This is still not helpful because it's equal to 6. So if we try to do any other method that we have worked with, this still becomes a problem. We need to find some way to deal with it. Well, hear me out. This is a trinomial. 1, 2, 3 terms. We have worked with trinomials, namely equal to 0, namely factoring. You got to factor this out. But it's more than just finding the GCF. It's more than that. So the little concept you need to be aware of when doing these problems is, hey, can I write all of these in terms of e to the x? So I'm going to say write exponential in terms of, let's call it a to the x, because you might not have base e, but you need to write it in terms of a to the x power. Which means in our problem, this is the issue. This is good. That's perfectly fine. That's perfectly fine. It's already in a to the x form. I need to write this in a to the x form. Well, we clearly know our base is going to be e. So already write e, and we want it to be in this form. The problem is we don't have e to the x. However, it is e raised to the 2x. This 2 is multiplying the x. If we remember on our properties, if I raise this to the second power, they are the exact same. And then I can just write this out. Minus e to the x minus 6 equals 0. Well, now let's look at it again. Let me just rewrite that again just so you guys are more aware. E to the x squared minus e to the x minus 6 equals 0. What is so special about this? Doesn't this look very similar to, let's suppose this was x, this suppose was x. Doesn't this look very similar to x squared minus x minus 6 equals 0? That kind of form? It looks very, very similar, which means we can factor it out via trinomial. So if you factor via trinomial, you'll notice that the factors of minus 6 that adds up to 1, minus 1, they're going to be exactly, and if you want to relate this to the actual factoring that we're accustomed to, this is x squared minus x minus 6 equals 0. If you want to see that resemblance, by now you guys should be comfortable with enough that it doesn't have to be an x anymore. It could be a y, it could be a 2x, it could be an x plus 3, it could be whatever you want. So the factors of minus 6 adds up to negative 1, they're going to be negative 3 and positive 2, which means that if I wanted to factor this out, I can do it by guess and check, or I can do it the long way. I'm going to do it by guess and check real quick. So it's just going to be e to the x minus 3 times e to the x plus 2 equals 0. Okay? Well, now that and you can show by the long way, showing your work by grouping and all that, you'll get the same result. Now, these are equal to 0, which means the way we can actually solve for x is we can set e to the x minus 3 equals 0 and e to the x plus 2 equals 0, which means the first one right here says e to the x equals positive 3, e to the x equals negative 2 in that case. Well, that should give us insight on how to solve this. Already you see some issues. So, now that I have this, let's apply our log rules real quick. If I want to apply my log rules, I'm going to apply natural log to both sides. Boom. I apply it to both sides. And then this cancel out. X is equal to ln of 3. It cancel this out. X is equal to ln of negative 2. Now if I try to actually put this in a calculator to get it out, ln of 3 is equal to 1.09. So x is equal to, it's roughly around 1. Let's just say 1.1. That's perfectly fine if I'm rounding to 2 decimal places. And then the other one was ln of negative 2. But wait, it says undefined. Why is it undefined? Why is this undefined? Well, you can't have a negative input for your natural log. Remember, the domain is strictly positive. I can't find an x value that'll eventually get this to negative. Even if I choose x to be negative, that won't give me a negative output. That does not. So that's the reason why this is not a solution. Or I'll say not a solution. Extraneous. If you remember that word, it's an extraneous solution in particular. It's a solution that algebraically works out, but if I plug it back in or if I do anything, it does not work. So your solution in this case is x is approximately 1.1. So you got to be sure you're able to do that. Now, these are some certain problems that might give you struggle, so be sure you identify that it is a trinomial that you're working with and use this idea. Write the exponential in terms of a to the x. I can easily give you something like 2 raised to the 4x and then minus 2 raised to the x, and then I don't even know. I can do something crazy like that. But it's on the table, so you got to know how to do it. Or I should put 2x here. But maybe I did 3 times this guy right here. Maybe I did something like that, and then minus I don't know, 4. If I were to ask you this, you would have to know that you set each of them raised to 2 raised to the x squared, and then minus 3 times 2 to the x, minus 4. And then this is the same thing as saying x squared minus 3 minus 4. And you can solve that. You can solve that. The factors are negative 4 and positive 1. You can work with it. But just because it has different bases does not mean we cannot work with it. You need to be able to know how to solve these problems. Alright, so that covers that. Now, that covers it all for exponential equations. Now we move on to the last thing, which is solving logarithm equations. These are much more simple. We don't have to worry about all that quadratic stuff happening. We do have some quadratics that play into this, but it doesn't get any messier than the other problem for exponential. So we need to be able to solve equations like, let's say I have, let's say ln of x equals 8. This is a very simple one because it's already isolated. We follow the same exact rule. Isolate, log, apply, instead of inverse log, you apply inverse exponential, and then solve it out. Same exact rules, it's just that our inverse is different. We're going to be using the exponential function instead of the inverse. Remember, these are exponents at the end of the day. These are exponents. So, what base for these exponents would be the inverse function? Well, natural log has base e, so I'm going to apply, these are exponents, so I apply the base e raised to, and I'm going to just use parentheses so you guys are aware of what's happening. Ln of x and 8. I apply that base e to these logarithm equations. Well, if I apply base e, this guy cancels out nicely. So I'm just left with x is equal to e raised to the 8th power. And you can calculate this in your calculator as well. E to the 8th power, what is that? E raised to the 8th power, that is 2,980. And let's say 2,981 if I round, or 2,980.96. So x is approximately 2,980.96. But we're able to calculate that, thankfully. Boom. And this makes sense because this statement is e raised to what power, or I'm sorry, e raised to the 8th power equals what? So boom, we're able to calculate that out. Now, let's move on to something more challenging. Let's say I have something along the lines of log x squared plus 1 right here. Oops, let's not work with that. Let me use a different one. Let's do log. Oops. I don't like these font sizes. So I'm very picky on that. Let's use log of x minus 2 plus log of x minus 3. And let's just set that equal to log of x squared plus 1. I just move the left to the right side instead. So we have this right here, this equation. Oh, I see a lot. So what you need to do additionally to isolate this, the problem is, yes, it might be isolate, but also combine logs if necessary. If necessary. Combine the logs if necessary. Well, over here I have addition. This is positive. This is also positive, technically speaking. Remember, they all have the same base. These are all common logs over here. If they're all the same base, I can actually combine them under one log. Now, because they're both positive, they're both multiplying each other. There is no division. If it was subtraction, we would be dividing that term out. But this is just x minus 2 times x minus 3 equals log x squared plus 1. Well, now, the logs are isolated, thankfully. They are isolated, which means I can apply my inverse exponential function. The common log base is base 10, so remember, these are exponents. The entire thing is an exponent. That means I can apply base 10 to each of these. Equals base 10 log of x squared plus 1. I can apply this out. If I wanted to apply this, what we notice is that, hey, these guys cancel out nicely, so I'm left with x minus 2 times x minus 3 equals x squared plus 1. Boom. Now, if I wanted to factor this out or anything, these are already factored as much as possible. This guy can't be factored out nicely. So what you might have to do is you might have to distribute. So let's distribute this out or expand. Boom, 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 boom. We get x squared minus, what is that? 5x plus 6 equals x squared plus 1. And now we're just solving a quadratic equation. We should know how to solve this by heart. I'm just going to subtract both sides. These guys cancel out if I subtract x squared. And I'm left with negative 5x. And if I subtract the 1, I get minus 5 equals 0. Factor out minus 5, I get x plus 1 equals 0. X has to be equal to negative 1. So, it works out nicely in that aspect. Oops, did I write this wrong? No, I wrote this. Let's see. Nope, I did good. Boom. Now, you have to plug this value in. You have to check. Because the reason why you have to check this more than your exponential is, hey, these values right here, these logs, I have to make sure it fits in my domain. Does it fit in your domain? If I plug in negative 1, do I get a negative input? You have to be careful on that. Sometimes they might not have solutions. You have to be very careful. If I plug in negative 1 minus 2, well, that's negative 3. I can't plug that in. So this is actually not a solution in this case. Not a solution. So you have to be very careful on your domain. Does not satisfy domain. Well, let's do another one just for more practice then. Just for more practice, since that one didn't work out nicely. Let's do the example. 4 plus 3 log 2x equals 16. This problem right here. Well, let's isolate the log first. I'm going to subtract 4 to both sides because there's 2 terms, and I need to get the log term by itself. So I get 3 log of 2x equals 12. Divide both sides by 3. You can do that. I get log of 2x equals 4. Now, it's isolated. I'm going to apply the base log 10. That's the inverse log to both sides. These cancel out nicely. I'm left with 2x is equal to 10 to the 4th. X is equal to 10 to the 4th divided by 2. That is your value. If I were to plug in here, you would see it works out nicely. So you can verify that for me, but this should work out nicely. This is 10. 10 to the 4th divided by 2. If you want to calculate that, it's a big number. 10 raised to the 4th divided by 2. That's 5,000. So we have 5,000 as our value if we raise that to the exponent. Boom. So that covers it for solving exponential equations and solving logarithms. Next time, we'll introduce at using these ideas to solve for compound interest. If instead of asking you for the accumulated amount, I ask you how many years, or I ask you what is the rates, interest rates. So you're going to be using logs and exponentials to actually solve these kinds of problems. So I'll catch you guys later. Take care. Bye.